Hello, mathematicians. Today we're going to talk about limits at infinity. What does that mean? Well, let's consider this function. As we're going to positive infinity, the limit as x approaches positive infinity, what is our x value approaching? Well, as our x value gets bigger and bigger and bigger, we see we're going to 3. And on this graph, we see we're going up and up and up, but we're never quite passing this horizontal asymptote, 3. So our y value is approaching 3. And as x approaches negative infinity, we're looking at what's happening as x gets smaller and smaller. As we go towards negative infinity, we see that our values are also approaching 3. Likewise, we can see that on the graph. So the limit as x approaches negative infinity of f of x is 3, because that's what our y value is. So the concept of limits as x approaches infinity means what happens to y as x gets infinitely large, or as x goes farther and farther to the right, what's the y value? And when we talk about negative infinity, is what's happening to the y value when x gets further and further to the left. Note that it makes no sense to talk about the limit as x approaches positive infinity from the right, because there is no number bigger than positive infinity. And as x goes to negative infinity, we can't say what's that from the left, because there's no number smaller to the left of negative infinity. So let's look at some graphs to practice finding limits at infinity. So as x approaches infinity, means we're going to the right. As we're going to our right, the function is increasing. And it doesn't stop increasing, so the limit approaches infinity. As we're going to our left, we're going to the left side, we're also going up and up and up. So that's also approaching infinity. So the next one, as x approaches positive infinity, what do you think it is? As we go to the right, what's happening to our y values? We're going down and down and down. Even past this graph, we keep going down to negative infinity. And on the left side, as x approaches negative infinity, well, we keep going up and up and up to positive infinity. In this graph, as we go all the way to the right, looks like we're approaching a certain value. We're getting closer and closer to this horizontal asymptote at -2. So our limit approaches -2. What about as x approaches negative infinity? What are we approaching there? Well, we're going to the left all the way to the end of the graph. And further on, it looks like we're getting closer to 4. In this case, we have oscillating behavior. We're going up and down. So you might be tempted to say the limit does not exist. However, if we look, the amplitude of this wave is getting smaller and smaller. The amplitude is approaching 0, so we're getting closer and closer to this line at y equals 0. On this side, as we approach negative infinity, what's happening? Our amplitude is still decreasing, smaller and smaller to 0. So what y value is it approaching? It's approaching 1. In this case, we have oscillating behavior as well. But our center line here is increasing. As we go to the right, we keep going up and up and up. So our limit is, as x approaches infinity, of f of x is infinity. As we go to the left, our amplitude is staying the same. We still keep going from -4 to +4, to -4 to +4, to -4. It's going back up and down and up and down. So in this case, the limit does not exist. Let's look at it from the functions. Limit as x approaches infinity of 5 minus 2 divided by x squared. Well, we have 2 divided by, and we're going to put infinity in our denominator. Infinity squared is just a bigger infinity. So we have 5 minus 2 divided by a really big number. That would be like if you have 2 pizzas and you divide it into an infinite number of pieces, like think 1,000,000 pieces. You have 1,000,000 people who need to eat 2 pizzas. Each person is going to get a very, very, very small amount. So this, any number divided by a huge number, is going to approach 0. So this will approach 5 minus 0, which is just 5. Now, if we have limit as x approaches infinity of 2x minus 100 over x plus 1. If we plug in x here to x, if we plug in infinity here to x plus 1, infinity plus 1 is basically infinity. Even larger numbers like 100 don't have a huge impact because infinity is such a big number. So we can kind of cross out these constant terms. So if we look at this, this becomes the limit as x approaches infinity of 2x over x. Now these x terms will cancel out, so we just get 2. Let's compare 3 different rational functions here. So here we have limit as x approaches infinity of 2x plus 5 over 3x squared plus 1. Again, we can cancel our constant terms. Anything that's smaller than the degree that you have crosses out. So we're left with the limit as x approaches infinity, 2x over 3x squared. So that becomes limit as x approaches infinity of 2 divided by 3x. So we have a really big number in our denominator again, so that is 0. In this case, when we cross these out, we cross out our constant terms, we notice that we have the same thing in both the numerator and the denominator. We get limit as x approaches infinity of 2x squared over 3x squared. These both cancel out, and we're left with 2 over 3. In the final case, constant terms will cross out. They're negligible. So we get the limit as x approaches infinity of 2x to the 3 over 3x squared. When we simplify this, we get limit as x approaches infinity of 2x over 3. In this case, we have a really big number in the numerator. And if we're dividing an infinite amount of money by 3 people, everyone's going to get like an infinite amount of money. So that's still infinity. So as a general rule, if the degree of the numerator is less than the degree of the denominator, like we had in the first case where we had 1 and 2, then the limit of the rational function is 0. If we have the same highest exponent, or the same degree in the numerator and denominator, then we're just going to take the ratio of the leading coefficients. And finally, if the numerator has a higher degree than the denominator, like in the final case, then we're going to approach positive or negative infinity. Note, if we had put negative infinity here, then 2 times a negative number divided by a positive number would be negative infinity. So the results from positive and negative can differ also if it's not just infinity. Let's look at this example. So we want the limit as x approaches infinity of 3x minus 2 divided by the square root of 2x squared plus 1. The constant terms we can cross out. So we're left with the limit as x approaches infinity of 3x divided by square root of 2x squared. Well, we have square root and x squared. So we can cancel those out, but be careful with your sign. Whenever you have a square, it makes it positive. So that will be 3x over square root of 2, making it positive, so absolute value of x. Actually, the definition of the absolute value of x is the square root of x squared. So now this will still cancel out, but we have to pay attention to our sign. When we plug in positive infinity, we'll have positive on top and positive on the bottom. So we will get this is equal to 3 square root of 2. If we're plugging in negative infinity, though, we'll still get limit as x approaches infinity of 3x over square root of 2 absolute value of x. But now when we plug in a negative in the numerator, we're going to get negative 3, and a positive in the denominator, we'll get negative 3 over square root of 2. So be careful with your signs. Now the reason why we do limits at infinity is that it helps us find horizontal asymptotes. So the line y equals L is a horizontal asymptote of the graph of f of x if the limit as x approaches infinity or negative infinity of f of x is L. So let's find some horizontal asymptotes here. Using our rules above, we can see the denominator has the bigger degree than the numerator. So we can say our limit as x approaches positive or negative infinity of 4x plus 5 over 2x squared plus 1 is 0, using the rule that we found above. The denominator is bigger degree than our numerator. And 0 can't be positive or negative, so we don't have to worry about the sign. That means our horizontal asymptote is y equals 0. We find the limit as x approaches infinity here of 4x squared plus 5 over 2x squared plus 1. While our constant terms cancel, we have the same degree in our numerator and denominator. So that's just going to be 4 over 2. And if we had put in negative infinity, we still have x squared and x squared, the same sign. We're going to get the same answer. So our horizontal asymptote is y equals 4 over 2, or just 2. In our last case, to find the horizontal asymptote, we're still going to find our limit as x approaches positive and negative infinity, 4x cubed plus 5 over 2x squared plus 1. In this case, our numerator has the bigger degree. So we're going to be approaching infinity. If we have positive infinity, then we're going to be approaching a positive number. If it's a negative infinity, then this will be negative infinity. So the limit as x approaches positive infinity of 4x cubed over 2x squared is infinity, and the limit as x approaches negative infinity is negative infinity. Going back to our horizontal asymptote, if we have positive or negative infinity, that means there is no horizontal asymptote. Let's look at this last example. So we want the limit as x approaches infinity, 8x minus 1 over square root of 2x squared plus 1. We're going to cross out our constant terms. We get the limit as x approaches infinity of 8x over square root of 2x squared. Remember, squared and square root combine to make absolute value of x. So this is the limit as x approaches infinity of 8x over square root of 2 absolute value of x. So when we plug in infinity and infinity, they will cancel out. We'll have a positive in the top and a positive on the denominator. But if we were to plug in negative infinity, square root of 2 absolute value of x, our denominator is positive, but our numerator is negative. So in this case, we actually have two horizontal asymptotes. Y equals 8 over square root of 2, and y equals negative 8 over square root of 2.